Hi, everyone. Welcome back to E54. Today, we're going to talk about Lecture 8. So we've sort of been working our way through the stress strain curves. We started by talking about elastic properties of materials, so just where we're stretching on those atomic bonds. We then moved up a level of complexity and further along in the stress strain curve by talking about plastic deformation, even taking a chance to discuss how we can change our material to affect that yield strength of the material. Today, we're going to primarily keep moving on complexity. We're going to talk about how our sample actually fails. And we're also going to introduce a few more complicated ways of deforming our sample. We'll talk about fatigue, where it's cyclic loading. And we'll talk about creep deformation briefly, where that's deformation at high temperatures. Okay. So in terms of the first part, the fracture, we're going to learn a lot of important things. We'll be able to distinguish between ductile and brittle fracture. We'll understand why flaws in our material, so cracks that are pre-existing, are really important, and they give us the difference between the properties we observe in real life and the sort of theoretical properties of the material. They do this because they apply a stress concentration. And finally, we'll talk about the fracture surfaces, effective temperature, and things like that. So practically, oftentimes, we need to consider the risk of failure when we're utilizing materials. And it's important to acknowledge that how acceptable failure is depends widely based on the application, okay? So just as two examples, you could think about a turbine disk in an aircraft engine or some component in your phone, okay? For the first one, we absolutely cannot have failure. If this engine fails, this plane full of 200 people might crash and people die, okay? Compare that with your phone, right? If some interconnect or your battery or some other piece of your phone breaks, you go, oh, that stinks. And then you go get another phone. Phones are something that every X number of years people replace anyways. Okay, so it's sort of a semi-consumable type of material. It's not to say it's good. We don't want our phones failing after a week, but it's not quite the same consequence. Okay, and because of that, you'll see these different topics emphasized to different amounts depending on the applications. Okay. So today we'll talk about three particular ways that materials can fail. These aren't the only ones, but they encompass a lot of the situations we care about as materials engineers. The first is direct overload. So if I just I'm loading it monotonically, so I'm loading it once, and I deform it so much that it breaks. Okay, we would call this fracture. We'll also talk about material or processes which are dependent on the loading history. I mentioned the cyclic deformation, which we call fatigue. So if we talked in one of our Q&As about compressing and having tension go back to back, if we kept doing this cycle over and over and over again, that would be fatigue. We can also talk about time-dependent processes. So at high temperatures, we worry about something called creep. So for the fracture mechanisms, the first thing we can do is delineate between two different modes of fracture. We can have ductile fracture. This occurs when we have a lot of plastic deformation. And in this case, failure is somewhat gradual. Brittle fracture happens with little or no plastic deformation and is generally pretty catastrophic. On this slide, what I'm showing you these were originally some tensile sample that is being pulled in the vertical direction. And there's sort of three different options. Really what I want to draw your attention is to the far left and the far right first. So on the far left is a material that is very ductile, okay? What that means is that its ductility, measured either by percent elongation or the percent reduction in area, is very large. And in this case, we see that material has drawn down to a very sort of fine tip, and there's been a lot of change and deformation and alteration of the shape of that sample in this region. We can contrast that with what's on the far right. This would be a brittle fracture. So here it's basically just a bunch of atomic bonds broke. The sample doesn't look very deformed around there. And if we look at ductility, we're getting really small elongations to failure or reductions in the cross-sectional area. Now, these are sort of the extreme. It's not really possible to say a material is X% brittle or X% ductile, but these are sort of the ideal cases. And then, of course, you could have something that's somewhere in between. So this is an example of a fracture surface with what we might call moderately ductile. So you're getting quite a bit of change in the shape of the sample in this region, but then at some points you get these sharp fracture surfaces. So one thing that's important to mention is that this large ductility is actually important from an engineering standpoint, because what it does is it gives you a warning before fracture. So if I have a sample that's ductile, I can see that it's plastically deforming or measure it and understand that, okay, things are going wrong in my material. The sample might break soon. In contrast, a brittle material, since there's no deformation before, it sort of will fail without warning. Okay, so we're pulling it looks like it's elastic, there's not much going on, and then it can fail catastrophically. As just a few practical examples of this, so on this top, this is a picture of a pipe. So there was some pressurized gas or liquid inside of here. Increase the pressure. If it goes up too high or there's a flaw in the material, this pipe can break. Okay. In this case, it failed in a very ductile manner. So you can see that the pipe bent and bowed outward. There was a crack that formed there, but it happened gradually and it happened sort of shared in a large region. In contrast, if you had a pipe and it undergoes a brittle failure, it might break apart like this. So originally it was the same type of pipe, but in this case, once it started to break, that crack went everywhere throughout the material and it broke into 1,000 pieces. And you can imagine that is generally much worse. So for that moderately ductile fracture, you would see something in between these two extremes. So first, as we're pulling on the sample, it will start to neck. So that's that reduction in the cross-sectional area after our ultimate tensile strength that threatens to run away. But what actually happens is all the dislocations moving in there can interact with other defects in our material, and we can start to form voids inside of our sample. Those voids then grow and link up with each other. And eventually we have these defects extend out and we have final fracture of our material. Okay. So there's significant plasticity and just shape change, but there's also something happening on the inside of my material. Okay. That's sort of the distinction that I'm trying to draw here. And we can look at a fracture surface like this. So this is a real life fracture surface of a metal wire. And the idea here is that you can see that reduction in the overall shape, and you can also see this lip where these voids started to nucleate and grow. Now, in this case, this was from something, this is an example of how those voids can form. In this case, there were second phase particles that were in there that served as the nucleation sites. Just to visualize this a little bit more, on the left is a ductile type fracture. It often has this characteristic type of shape that sometimes people call a cup and a cone. So you can see that these two fracture surfaces fit together, but they're not sort of identical to each other. One forms a shallow recess, and the other one forms this sort of cone that would go and fill that in. Okay. The brittle fracture, on the other hand, they sort of look identical. There's not a whole lot of deformation besides just that creation of that fracture surface. You can see other evidence of those cracks growing in certain cases. And in this case, this one is showing crack growth from the edges and what are called chevron markings. So in this case, there was a crack that started here, nucleated there, and then all these sort of lines that we can see here on this picture, and which are drawn in the schematic down here, are showing you how that crack, which started at the edge, propagated through. You can see this. It doesn't have to start from an edge either. On this top example, this is two sides of a chunk of material which was pulled and broken, and here they're identifying that here and here there were internal regions where the crack started, and then those cracks moved out into the material. Okay, and then this is finally just another example. This one starting at the surface and moving down, zoomed in a little bit more. So brittle fracture can happen in multiple ways. It can actually, what's sometimes important is to think about how the crack is moving through your microstructure. We often said that materials are made of many crystals. So it turns out that those cracks can move along the grain boundaries. This is what's called intergranular fracture. So this is when the crack is moving between the grains along the grain boundaries. This is an example in steel. So this sample was etched, so you can see the outline of all these crystals, and the crack just was sort of following along in between them. It can also happen in other types of materials. So this is an example in polypropylene showing, so this is a polymer material, showing how that crack can move along crystalline boundaries. In contrast, you can also have what's called intragranular fracture. So this is where the cracks are moving around primarily in between or in the middle of the grains, so within the grains. And a good example you can see is right here. So there's a nice crack along this region, and you can see it going right through the middle of these three or four grains right here. This example is also from a metal. So these are both steels, different types of steel. What that means is they have different alloying elements in them. But it also happens in other types of materials. A good example here is this is for an aluminum oxide. So this would be a ceramic. And in this case, you see those fracture surfaces, but they don't follow the outlines of the grains. Just showing this from another view. On the top, there's a schematic. On the bottom, there is a scanning electron microscope image of fracture surfaces. So oftentimes when the crack follows the outline of the grains, you can actually see the outlines of those crystals in that image of that, if you look at that fracture surface afterwards. In contrast, it's much harder to pick out where the crystals are in this type of fracture surface. So it's important to recognize that all real materials have flaws and that these can affect the material behavior. So if we were to go and predict what the yield strength of a perfect material would be, and then even the fracture strength, so keep going on past that, of a perfect material would be. So just, we started with atoms and a crystal structure. Don't think about having any cracks or other defects in there. It would turn out that our material would be really, really strong. So its strength would be something like the elastic modulus divided by 10. Now, if you remember, the elastic modulus is somewhere in the tens to hundreds of gigapascals. So that would mean our strength of our material would be in the gigapascal range. Sometimes materials get close to this. So if you make really carefully made glass fibers, you get up somewhere near that. But most materials are much below this. So if I just make a typical ceramic, so something like that aluminum oxide, I often am about 10 times lower in strength. Okay. Even metals that are strengthened through all those mechanisms of solid solution strengthening, precipitation strengthening, grain size strengthening, work hardening, they still tend to be in this range of strength of Young's modulus divided by 100. So there's some sort of difference here. And the main point is that the strength of real engineering materials is much less than the strength of what you would expect if these things were perfect. Now, this was actually identified many, many years ago. So Leonardo da Vinci did this experiment. He was basically doing a tensile test, but he was taking and putting actual physical weights on the end of these wires. And he found that the longer the wire, the smaller the load for failure. Okay. And the reason for this is that flaws inside the material in the form of cracks and things like that can cause premature failure. And a longer sample would contain more of these flaws. So let's zoom in a little bit and think about this. So what really happens is that these flaws or these cracks inside of these materials actually serve as stress concentrations inside of our sample. So we're taking our sample and we're pulling on it with a stress sigma naught. And first we think that that's the stress inside of our material is feeling. But it turns out that if we have these little cracks, the regions near the edge of those cracks experience higher stresses. So if we zoom into this area and plot what the stresses are, if we're really far away, we'll be at that level sigma naught. But as we get close to the crack tip, we increase to some elevated value. And this is showing on either side of the crack tip. So in between, it's not plotting what the stress is because there's no material there. So this local increase in the stress is quantified by something called the Griffith equation. This is a famous scientist in this area. And this equation says that this max stress near these flaws is going to be equal to 2 times the applied stress. So this is what we're sort of applying to our sample globally. And then multiplied by this term, which has the crack length divided by the radius of curvature of that crack tip to the power of 1/2. Okay. Sometimes this is rearranged to put it in the to put it with just these simple terms. One has this K sub t, and this has the applied stress. So if you want to put it in this term, this capital K is showing you how much the applied stress is being magnified. So you can see a few things there. So if A is bigger, this magnification gets bigger. And if rho gets smaller, which means that the crack gets sharper, this term also gets bigger. Okay, so it's a radius of curvature. A small radius of curvature means a really sharp crack. So we could take this Griffith equation. This is just rearranged to get that stress concentration factor, that K sub t. And what this really emphasizes is that if that magnification factor is very dependent on the size and the sharpness of those cracks, you would really need to go and understand those flaws in your material to understand how much of an effect this is having. So let's think about an example problem. We're going to take a brittle material and we're going to go and estimate the theoretical fracture strength. If we know that these elliptical surface-shaped cracks of a given size are what cause propagation. We've measured them, so we know how long they are, we know the radius of curvature, and we know what our applied stress is. And the basic assumption we're making is that, well, that theoretical strength of our material wasn't wrong, it just wasn't accounting for these cracks. So we can go in and plug in these numbers. So what would that max stress near that crack be? We'll go in and plug in the applied stress on the material, that's a factor of 2, the length of the crack, and the radius of curvature, making sure that all of our units are canceling out. And what we'd find is that for an applied stress of 1200 megapascals, the stress near these types of cracks can be about 35 gigapascals. So if you want, this is 1.2 gigapascals, it's whatever that is, roughly 30 times higher. Okay. So just from an engineering perspective, that tells us something important. That tells us that we don't want many cracks. We want them to be pretty blunt. But also, if we're designing something, we're making some part, we're putting in stress concentrations there too. And if we did this, we would want to also avoid sharp corners. Okay. So I could go and do an experiment, make a little sample here. It's thicker at the top than at the bottom, and I have what's called a fillet here. So this is a way of making this corner a little bit smoother. And it turns out that if you make that more round, you're going to decrease the stress concentration that you see. Okay. So for any one of these curves, this is for a given ratio of the width to the second width, so W to H. You just pick one if you want. But as we move to the left here, this is going to a sharper fillet radius. So it could be a sharp corner, it could be a 90-degree angle, or it could be some smooth rounded corner. Rounded corner is out here, sharp corner is in here. So what you see is that you get a pretty rapid increase in that stress concentration. So those cracks also have to go and propagate. And it turns out that that sharpness of the crack forms is important for determining the difference between brittle and ductile failure. So in a ductile material, we can have lots of plastic deformation, and that can happen at our crack tip as well. So if we start with a sharp crack tip and we have a brittle material, there's really nothing else that this sample can do. We can't experience a lot of plastic deformation. So what happens is this crack just grows, bonds break, and the sample breaks apart. In a material which is ductile, we know that there can be plastic deformation in regions with high stresses. And those crack tips are stress concentrations, so that's where we're going to have a lot of plastic deformation. As that crack tip heavily deforms, it's going to become blunted, so it's no longer as sharp. which means that there's less of a stress concentration and our material is able to survive deformation a little bit better. Okay. So what's really happening in either of these cases is we're thinking about having an energy balance at the crack tip. So we think about this primarily in terms of what's called elastic strain energy. So there's energy stored in the material as we elastically deform it. If you want to think about this, you could think about it as a spring. So if we pull on a spring, there's energy stored there. If I release it, that spring snaps back. Okay. There's also energy released when a crack propagates. So if you want to think about this as a defect, the material would prefer to have all the bonds formed, and a crack is a slice through a material where those bonds are broken. If we increase the size of that crack, that's going to increase the energy of our system. Okay, and this really requires new energy. So for a brittle material, we can take that original equation that Griffith had and derive a relationship that determines what the critical stress would be for crack growth, okay, to get those cracks moving and propagating. So for a purely brittle material, you can basically isolate this and think about those elastic strain energies and identify that the critical event is creating new surfaces. So there's going to be some energy term, which is the surface energy. So what's the energy per area of creating new surface? And we'll also see some of our other terms here as well. So the size of the crack matters as well, as does the modulus of elasticity. Okay, so this is how much energy I can store with those stretching of the bonds. So this critical stress is equal to the square root of 2 times the elastic modulus times the surface energy divided by pi times the size of the crack. You'll sometimes see this rearranged where people take the size of the crack and move it onto the left side of this equation. So here we have what's our critical stress at times square root of pi times A. The idea here is that what you're doing is on one side of the equation, you're getting all your external variables. So what size are the cracks? What stress am I applying? Those sort of external things. And on the right, you're getting all your material properties. So square root of 2 times Young's modulus times the surface energy. If you had a given material, say I had a piece of aluminum, I would know what my modulus and my surface energy are. I wouldn't necessarily know these other things. These are external variables. Okay? When this equation is arranged this way, this left side is what's called the stress intensity factor, capital K. And this right side is called the fracture toughness. Sometimes this is called capital K sub C. Now, the reason this terminology is used is you can think of this fracture toughness as the critical value of the stress intensity factor where fracture happens. Okay? So this equation right here is saying what happens at fracture. But basically, if the stress was less than this, your stress intensity factor would be less than the critical value. Okay? Now, this type of equation was really formulated for purely brittle fracture. If you start thinking about ductile fracture, all you would really have to do is change this energy term. It no longer would just be the surface energy. It would be something like the energy associated with creating a new surface plus the energy associated with having plastic deformation. Okay? But the same idea holds. So the way this works in practice is we can go and take our material. We can think about having different shapes of cracks there. And we deal with this in a relatively empirical way. But oftentimes what we do is go and pool on a sample like this and measure that fracture toughness, that K sub C. And all I did was sort of think about it in terms of my external variables, okay? So I take a material, I pool it, I measure what's the stress where it breaks. If I know the crack size, I can predict what that fracture toughness K sub C is. The other thing I've added in here is some constant Y. You can just think of this as a correction factor. So that equation I showed you, Griffith went and derived that equation for the stress field around an elliptical crack in the center, okay? So if you have a center crack, that Y is just equal to 1, which basically means there's no correction, okay? If I have an edge crack, that Y is equal to 1.12. the way of thinking about that is saying, well, to make these numbers work for a different type of crack, I need to have a correction factor of about 12%. Okay. Now, you don't have to go drive these things. These correction factors are something that are taken from empirical evidence. People run a lot of experiments and find what fits the data best. But for example, here's a type of table you can look up for finding what that correction factor is. Okay. So for example, for a center crack, you get an equation for y, because Griffith assumed that his width was infinite. It was an infinite plate. Okay. And if you look at that equation, if I put in a super large number for w, these terms become vanishingly small, and y is equal to 1. Okay. You can keep moving down for other types of cracks, so that y, when the plate or that width is very, very large, is 1.12. And then there's these other Taylor expansion type of terms afterwards. And you can do it for other different types of cracks. So for double edge notch, and then even this is for an embedded, what's sometimes called a penny crack. So if you think about it, if you took out a chunk of material that's shaped like a penny in the inside of your material, this would be what your y, that dimensionless parameter, would be equal to. So that fracture toughness of your material usually has the units megapascals times square root meter. And this starts to tell us why we use metals so often in structural applications. So when we thought about elastic properties, we said metals and ceramics are similar, ceramics might even be a little better. When we thought about strength of materials, we said metals and ceramics are pretty similar. Ceramics might even be better when in compression. Tension's a different thing. And that comes about mainly because of this fracture toughness. So metals are the clear winner in terms of fracture toughness. They have very, very high toughness values, an order of magnitude higher than ceramics. Okay. And this is representative of the fact that metals are generally ductile and ceramics are generally very brittle. One other way to look at material properties is to try to think about how different material properties scale with each other or tend to correlate with each other. This is what's called an Ashby plot. So on the left side is the fracture toughness, and on the vertical direction is the fracture toughness, and on the horizontal axis is the strength of the material. This is the fracture strength. And what you can find is generally, I can say, well, stronger materials have higher fracture toughnesses. Okay, I guess that's true. But there's some deviation. Some materials follow along other lines and other trends. Okay? So generally, my engineering alloys are really high on the toughness on the vertical axis, and they do okay on the strength. Whereas the engineering ceramics do great on the strength and are just okay on the fracture toughness. So this tells you how we can delineate between these two different classes of materials. I do want to mention there's technically different ways that we can open these cracks inside of our material. What we were showing before was there being a center crack and we're pulling on the sample in the vertical direction. This is what's called mode 1 opening of cracks. You can also think about applying the stress in different directions. You could have it be applied in a shear direction and open the crack as well, or in a tearing type of direction. And these are just called mode 2 and mode 3, respectively. So again, if we're trying to design against crack growth, we really need to think about that fracture toughness of our material. And what we want to do is we want to ensure that the stress intensity factor felt near those crack tips is below the fracture toughness, because when it gets to that value, our material will start to break. Okay, this tells us that the largest, most stressed cracks grow first. So if you want to think about it in terms of engineering design, we can have a few different types of things. If we know our max flaw size inside of our material, that can dictate what stress we design this component to be able to feel. So if we know that our material has cracks of a certain size, maybe we figure this out with ultrasonic testing or something, and we know our material has a given fracture toughness, we go and we make our part so that the stress is never above a certain level. So if we do think about that, we can make plots where as we sort of think about what the max crack size is, we could pick out a given limit stress above which we would fracture and below which we're safe and we don't have fracture. Okay. We could flip that around. We could say, if we know what our fracture toughness of our material is, and we know that we need this part to be able to survive a given type of stress, that tells us that our cracks in the material would need to be less than a given value. So we might need to revisit how we make this material to ensure that that's the case. In this case, again, for a given stress level, if the crack size is larger, we'll fracture. If it's lower, we won't. We'll be safe. Just as an example, let's think about how you could use this if you're designing an aircraft wing. So we're making it out of some material with a fracture toughness of 26 megapascals root meter. And we'll think about how we could use this. So if we have designed aircraft wing type A, we measured it and saw that the largest flaw was 9 millimeters, and that when we tested this, the failure stress was 112 megapascals. We want to take this data and think about how we could then go and inform, if we made a different design, made it the same material with a smaller flaw size, what would our failure stress be? So we're just going to use that equation. We're trying to isolate what the failure stress is, so we'll start with that. And the key thing is to recognize that for both of these types of designs, we're using the same material and we'd expect the same types of cracks, so that Y in that K sub C are going to be the same. The things that are going to be changing are A and sigma. So one way to solve this is we can set we can rearrange these equations so that Y and K sub C are on the same side, set them equal to each other. On the left side, this is the data for design A. Plug in what the failure stress is, what the crack size is. On the right is the design considerations for design B. We could know the crack size and we're trying to solve for that sigma subcritical. We could go in and solve that this would be 168 megapascals. Now, there's different ways you could go about solving this. You could alternatively just take this equation, solve for K sub C, and then calculate what the critical stress is in 2 steps. That's reasonable as well. So one thing we've ignored up to this point is the loading rate. So it turns out that all of these things we're talking about are dependent on how fast we load our material. So if this is showing 2 plots of stress strain curves for the same material. In the blue curve, we're loading it slower. So the applied strain rate is smaller. And in the red curve, the applied strain rate is faster. So this is something where we take it and deform it really quickly. So increasing loading rate generally increases our yield strength and our ultimate tensile strength. It also decreases our elongation to failure. Okay? And the way to understand this is relatively simple. We talked about how dislocations have to move around inside of our material. They occasionally have to get past each other to keep plastically deforming. And the idea is if you deform your sample faster, you give it less time for dislocations to move past obstacles. So one practical way that we can measure the toughness of a material is through what's called impact testing. So this is a very severe testing case. It generally does make materials more brittle and decreases toughness because it's a high loading rate. But the idea here is you can take a sample. So this is some bar of the material. You put a surface crack into it with a designed size, so you know exactly how big it is. And then what you're going to do is you're going to impact this sample and break it at that crack notch. There's a few different ways you can do this. On the bottom is showing the idea. You have your sample there with the crack there. A hammer comes through. You put it in a given starting position, so you know its potential energy. You let it go. It hits that sample, uses some energy to break it. Then you can look at how far it goes and see what its potential energy is over here. The lost energy went into the sample. There's 2 general kinds of tests like this that people do. One is called the IZOD, the other called the Sharpie. The only difference is how is that sample arranged down in this testing table? It could be sticking up loosely, so this hammer comes and hits the top and breaks at that crack. Or you can have this sample bent over some sort of opening where it comes and smacks on the other side of the crack. They're not dramatically different. Anyways, if you did some sort of test like this and you went and looked at how much energy was lost in this type of experiment, you could go and measure if it's a little or a lot. But what's nice about this is you could go and do this type of measurement at different temperatures. And generally what you would find is that at low temperatures, the amount of energy dissipated is very low. And at high temperatures, it's very high. And there tends to be what we call a ductile to brittle transition temperature, where it shifts between the low and the high values. Okay, so turns out that when we were saying is a material ductile or brittle, you would even need to know more. So you would need to know what temperature is it tested at. Here's a good example. So most metals, we said they tend to be pretty ductile, and that's true at our ambient conditions. Okay. Two very well-known examples are the Titanic and these Liberty ships in World War II. These were made of materials which were ductile when these things were fabricated, but then they were used in areas of the Atlantic Ocean where the temperature was much lower, and the material actually went into that brittle regime. So they were below their ductile to brittle transition temperature when they were used. So increasing temperature ends up increasing the elongation to failure and the fracture toughness of your material. And on the bottom here is sort of just showing you some examples of how that impact energy can change with temperature. So these are all for metal samples. On this top in this green curve is showing face-centered cubic metals. There's lots of possible slip systems. It's easy for dislocation to move around. So it turns out that most of the temperatures we care about, these materials stay very, very ductile. Okay? It's hard to make it brittle, hard to get it cool enough to make it brittle. On the other extreme is this blue curve on the bottom. These are really high strength steels and alloys. It turns out that these stay pretty brittle. Okay? Even if I heat it up, that impact energy only increases a small amount. Something that's sort of in between are things like body-centered cubic metals. So for example, we can say iron at most relatively modest temperatures, so places we'd use it in everyday life. This ductile to brittle transition temperature might be reasonably accessible during applications. So we really need to think about, is this material brittle at room temperature and ductile at 100 degrees Celsius higher? These types of behaviors can also be affected by other aspects like the purity of the material. This plot right here is showing data for impact energy versus temperature for steels with different carbon content. Okay, so these materials are all brittle, low impact energy required to break at the really low temperatures, but that temperature at which they transition is a strong function of how much carbon is in the sample. Okay, so for very low levels of carbon, this ductile to brittle transition temperature is relatively low, but also this impact energy jumps quite a bit. It jumps from a very low value to over 300 joules. Okay. In contrast, as I add more and more carbon, this transition happens later, and then the difference is much smaller. Okay. So if you think about this, room temperature is somewhere here, right? So if I take a steel with a very low carbon content, I'm going to expect it to be very ductile at this temperature. But in contrast, if I look at a steel which has a lot of carbon in it, I'm still going to measure that it's brittle. Okay, so not every steel is the same. We need to think about all of the different things we can change, and alloying is an obvious one. So let's do a quick little quiz. So that local stress intensity blank as the radius of the crack tip increases. So as the radius of the crack tip increases, what happens? Okay. It could be not affected. It could vary directly proportional, very inversely proportional, increases or decreases. The equation we would want is that Griffith fracture equation. So the local stress intensity is that K parameter. Okay. The radius of the crack tip is on the bottom here. So as this increases, we know that this overall thing is going to decrease. So not affected is wrong, increases is wrong, and directly proportional is wrong. And this factor of 1/2 tells us that it's not inversely proportional. Okay. So as that crack tip radius increases, our stress intensity factor decreases. So the cracks are blunter, the stress intensity factor goes down. We'll ask a similar question. So the local stress intensity does what as the length of the crack increases? Similarly, we can look at the same equation. As this value increases, now that stress intensity increases as well. All right, so coming to the fact that up till now, we've been talking about sort of taking our sample, loading it until it breaks. That's not always the way we load real engineering materials. We can also have what's called fatigue, which comes from variations of stress with time. So we can think about loading our material in tension, putting it in compression, tension, compression, and keep doing this over many times. This is showing a pretty regular type of variation between tension and compression. Oftentimes, we'll think about some different ways of measuring this. Sometimes you'll see people talking about the mean stress. So what's that average stress there? What's the amplitude of the stress? So how much does the max go above that mean? And then also sometimes people talk about that full range at which the stresses vary. Okay. Now, one thing I want to point out is that these two top curves are showing very regular changes in the stress. That doesn't have to be how our material is actually loaded in reality. It can be this sort of jagged, unpredictable way as well. So these can be very important. Good examples of applications are things like in your car axle. So this axle is spinning. You're going to get cyclic variations in tension and compression in that axle. And then you'll also get a regular type of loading when you go over things like a bump or a pothole in the road. This also happens in things like planes. So for example, when you get wind gusts, you can get different loading conditions on the wings of planes. And oftentimes you also have to think about vibrations. So sometimes you can have your wings vibrating and having low loads at very high frequencies. So one of the ways we can actually test this, if we take a material we want to understand this type of behavior, we can do what's called a rotating bend test. In this case, the sample is put in the middle. A load is put on it, so this material is bent. And what happens in this case is that this part right here is in tension and the top is in compression. Now, you could do a bending test where you just bend a sample until it breaks. In this case, what they're doing is they're taking and they're spinning that specimen inside of this. So if we follow some little region on the sample, if we're at the top originally, that region at the top is in compression. It's going to rotate around and eventually be in tension, and then rotate around and eventually be in compression. And it's going to cycle back and forth between those states. Okay? So this is just showing what that stress strain curve might look like. It's going from a maximum to a minimum. We already talked about the mean. One thing I want to point out is that sometimes these curves refer to that stress amplitude, so how much we go above or below the mean, as S as well. So some of the key points of fatigue is that this type of loading can cause failure even when the maximum stress that's applied is less than the yield stress. Okay, and really a practical consideration is that it's been estimated that roughly 90% of engineering failures come from fatigue. So it's a very important type of deformation. Now, part of that has to do with how well we understand yielding. So if you design a material part and it fails through yielding the first time it's used, you're a very engineer. No, the sample's loaded up, keep it below its yield strength, okay? The issue with fatigue is it's a little bit harder to predict, right? So, and you're also talking about something happening over maybe years. So it's more difficult to predict, which tends to be why it leads to more failures. So a common way of plotting this type of data is to take your material and understand how it fails in that type of rotating bend test. And you'll change your experimental parameters and get something that looks like this curve. So this is what's called an SN curve. So it's the stress amplitude and the number of cycles to failure. And then if you populate this, you would get data following along this red line. Okay? So sometimes materials exhibit what's called a fatigue limit. And what that means is that as the stress amplitude gets below a certain value, the sample can survive forever. Okay. So as a designer's perspective, what that would tell you is that you want to keep, as long as you keep that stress amplitude below a certain level, your material is safe forever. A good example is a lot of steels demonstrate this type of fatigue limit. It is important to point out that that's not true of all materials. So for example, aluminum doesn't have that limit. So it still has this behavior that as I reduce the stress amplitude, I can survive for longer and longer cycles, but there's no sort of flat region of this type of curve. Typically, we describe what's happening during this fatigue type of deformation with what's called the Paris law. And this talks about how do cracks grow during that cyclic loading. So what's in this equation is the derivative of the crack size, A, with respect to the number of cycles. So you can think of this as how is the crack length increasing per loading cycle? This delta K is actually what's the change in the stress intensity factor that we learned about before during this loading. And what this means is placing an emphasis on those local stresses near the cracks. Now, this is going to be something like the change in the stress, so that'd be the stress range or amplitude, multiplied by square root of pi a. So this looks a lot like that value K we saw. Now the unknown, the empirical thing here is some material constant m. So this is the delta K to the power of m. Now for most metals, this is typically in the range of 1 to 6. On the bottom here is just showing an example where this was a rotating shaft, an engineering component. It had a piece cut out because the component needed that. So it effectively had a flaw, but the sample failed because the crack grew, even though that local stress intensity factor was below the fracture toughness of the material. Now, generally, cracks are going to grow faster as that delta sigma increases. So as the stress cycles get larger, it's going to grow faster as the crack gets longer and as the loading frequency increases. So if you want to think about this, these are all talking about more extreme deformation scenarios. You can see evidence of this on these crack surfaces. Before, when we looked at a crack surface, we saw crack start and then all these long fracture surfaces. Now there's a lot more nuance in this picture. So right here, what's happened is that, or sorry, right here, what happened is the crack nucleated, grew, and then fractured. I'm sorry, I have this upside down. The crack nucleated here. It grew gradually as you went this way, and eventually got so large that this happened fast fracture. I apologize, these two pictures are flipped. I confused myself. Anyways, if you zoom in on this region right here, what you'll find is all these striations where each of these is one cycle, and the crack grew a little bit through that material. And here you can see that on the schematic. The crack is growing a little bit each time until it's so big that it breaks. So if we want to think about resisting this fatigue, we can do a few things practically to sort of make our material better, able to avoid this fatigue failure. One way is we can impose compressive surface stresses on our material. So when we notice that if we go and we take these SN curves for a bunch of different materials and we change what the mean stress is, we'll notice that as we increase the mean stress, so we're making this deformation more and more tensile in nature, these curves will shift to the right. Okay? One way you can think about this is that for a given stress amplitude, the number of cycles I can survive goes down pretty dramatically. Okay? And the idea here is that tensile stresses are really the cause of the problem. They're the ones that are trying to open up those cracks. So when we add a compressive stress, it sort of counteracts this. There's a few ways that are really common to do this. One is through what's called shot peening. So the basic idea is you take your component and you smash the surface of it with little counterbodies. They're hard particles often. And what those do is they put the surface into a compression state. And in that region, the cracks are going to have a hard time growing near the surface. Another way of doing this is what's called carburization. We mentioned this, we talked about gears. We talked about carbon diffusing into our sample. So in this case, we have a carbon gas on the outside. We have diffusion into the material. And what this does is it puts this outer layer into a compression. Okay. Another thing we can do is we can really be thoughtful about removing stress concentrations. So basically, what we learned from fracture is that stress concentrations are bad. So having cracks in there or having a sharp machined surface into our material is bad. And fatigue just makes that stuff worse. So we can use that same type of idea. So if we can go from a sharp corner in our part to a fillet radius, this is going to be better against fatigue. Okay, the last thing I want to talk about just very quickly is what's called creep. So this is deformation at high temperature. So in this type of experiment, we'll think about taking some sample of a material we care about. We're going to apply some load, so some sigma value, and we're going to keep that stress constant. Okay. So on the right here is showing that before time zero, there's no stress on the sample. We increase it to some finite stress value and we keep it constant. Right? Now, at low temperatures, we would expect the sample to maybe elastically deform, maybe even plastically deform, but then stop. Okay. At high temperatures, that assumption that everything is static starts to fall apart. If we do this type of deformation at high temperatures, we'll get the instantaneous deformation. So maybe that's that mixture of elastic and plastic that we have. But if we let the sample sit there, we'll find that it will keep elongating. And it will follow this type of shape where it happens relatively fast. There's a sort of what we call a steady state or secondary type of creep. And then finally, it ends up running away and fracturing. Okay? So while we thought our sample was safe because we're below the fracture strength of our material, it's going to actually break. These different ranges are talking about the width. It's very important to talk about what's happening to the slope of these curves. So in this primary creep regime, the first one, the slope is decreasing with time at first. This secondary or steady state region is the one we care about the most, so where it's linear. And then finally, this tertiary region runs away and breaks. So this creep happens at elevated temperature, and it turns out this type of behavior is very, very dependent on the temperature that we use. So this example on the bottom here, this yellow curve, is showing you what happens at low temperatures. You basically get some elastic deformation, maybe some plastic relaxation. So you've given it some time for dislocations to rearrange, and then the strain just stays flat, never breaks. If you increase the temperature above this range of about 40% of the melting temperature, you start to see these creep type of curves. And as you increase the temperature, what you find is this creep deformation happens faster and your sample breaks earlier, so at lower times. Okay. So in a sense, I started by saying this behavior happens at high temperature. High is a subjective word. What I mean by high is usually about 40% of the melting temperature. So of course that means that that exact temperature varies depending on the material you're looking at. If I compare something like aluminum, which has a low melting temperature, and tungsten, which has a very high melting temperature, a given value of degrees Celsius might be very different. So for example, room temperature can be reasonably high for aluminum, but it's a very, very low temperature for tungsten. That's often why we think in terms of what fraction of the melting point are we at. So in that secondary creep regime, that dashed line right here, we do have an equation to describe how our material deforms. So what we often want to describe is what is the strain rate. So if the stress is constant, what is the rate at which that sample elongates? So that strain rate is going to be equal to some material constant times the applied stress to the power n multiplied by some exponential term. And inside that exponential is the usual things that we'd expect from an Arrhenius equation: negative and activation energy divided by R times T. Now, where did we see these types of exponentials before? In diffusion, right? Turns out that that's not a coincidence. The reason we see it in this type of equation is that diffusion is a very important part of what's happening during creep deformation. So what you would find is that the strain rate increases for higher temperatures and stresses. This plot right here is showing how the steady state creep rate changes with stress. So it follows this exponential type of curve because this is a log-log plot. So it looks like a straight line here. And then as the temperature increases, the stress needed to give a certain strain rate goes down, which means it becomes easier to have creep deformation occur in my material. So if we do creep failure and deform at this high temperature, we can also go and look at the fracture surfaces. One common thing is to find that failure happens along those grain boundaries. So these are those interfaces between different crystals, and these are where cavities started to open up and form. So oftentimes people care about things like, if I have a component under a given set of situations, how can I predict its lifetime under those creep conditions? Just as an example of how people might think about this, so you could be asked how you could estimate the rupture time for a given type of iron at a given temperature, 800 degrees C in this case, at a given stress of 20,000 PSI. What you would need to do is gather some information on your material. In this case, it's already gathered, so I'm just showing you a plot of this. This plot is showing on the vertical axis stress, and on the x-axis, this term L, which is called a Larson-Miller parameter. Okay, and this is something that tries to combine what's the effect of the temperature and the time on these types of creep deformation. So really what you need to go and do is know what this curve looks like for this given type of material. But in this case, if we know what stress we're at, we could read off this curve, go to 20,000 PSI, come down and see that this Larson-Miller parameter would be 24 times 10 to the 3. We know what temperature we have. An important thing is that whenever we're talking about temperature, we often want to go to absolute units. So instead of 800 degrees C, we're going to put this in terms of Kelvin. So it's going to be 1073 Kelvin. And we can go and solve for what the rupture time would be. In this case, it's 233 hours. Okay. So this is the type of prediction people might need. You wouldn't have to derive this because this was something people figured out from many experiments. But you could be given data like this and asked to read off and figure out what a rupture time is. Okay, so just to summarize, we've talked about how engineering materials are not as strong as predicted by theory. And it turns out that this connects to the fact that flaws act as stress concentrations inside of our material. Sharp corners can also produce large stress concentrations and lead to premature failure. So we need to avoid having large cracks and avoid having sharp corners. And then that the failure type we see can depend on the temperature and stress that's being applied to our sample. So for simple fracture is really what happens when we have non-cyclic stress and low temperatures. And this fracture stress increases with maximum flaw size, decreases with temperature. Fracture stress decreases as the max flaw size goes up. It decreases as the temperature goes down, and it also increases with the rate of load. Fatigue is when we're having cyclic type of deformation. And in this case, this is what happens when what we really care about is how the cycles to fail decreases with the change in the stress. So the stress cycles that our material feels. Creep is what happens at high temperatures. And generally that time to rupture decreases as stress or temperature increases. So if we increase the stress on our sample or increase the temperature it feels, it's going to take less time to break. All right, that's the end of today's lecture. Thanks for joining us. I will see you soon in a Q&A session.